Good afternoon, everyone. And it's the last talk of the day, I know that, so half of you will be happy for my talk because of the drinks afterwards. The other half will be happy because of the drinks afterwards again. So that's the only two options, so please bear with me. So I'm Sipitanou, I'm the head of business development for Copley Scientific, and today, kind of picking up from parts of where Jamie left it, we're going to discuss about DPI's testing. And I'll focus a bit more on the QC side of things, but of course everything applies on R&D as well. Just a few words about us before we begin. Copley Scientific is the world leader in manufacturing and supplying instrumentation for inhaler testing. So if any of you is not in the inhaler testing field, we are one of the leaders, if not the leader in the field, but we also do supply equipment for other solid dosage forms, such as tablets, capsules, etc. We've got global presence, and you probably have come across our equipment in all of the labs of companies that develop inhalers. All right, then. So when I first joined the inhaler industry a few years back, everything was a bit confusing in terms of different devices, different dosage forms, liquid, dry powders, etc. So I tried to put together a table just to kind of explain to my head and then to people what's going on. So just to give you an overview of the devices and products that are out there, we've got the liquid products under which fall the MDIs, the nebulizers, and the aqueous droplet inhalers, or elsewhere called SMIs. Now, the common characteristic of these all is that they're active devices, meaning that the aerosolization is not that dependent on the breathing of a patient. They have some sort of mechanism, so either propellant or power, that help with the aerosolization of the product. And what matters here is coordination. Whereas when we go into more dry powder inhalers, which is something that we'll be discussing today, the key characteristic is that they're passive devices, meaning that they have the only source of aerosolization will be the human breathing. So they're passive, and they highly depend on the breathing flow rate. And why I'm saying that is because you'll be seeing it a lot into not just the clinic, but also into your testing, and how this flow rate dependence really is illustrated during the testing. Now, in terms of the different DPI products that you might see in the market, I've categorized them in two categories. The first ones are unit dose inhalers, unit dose DPIs, meaning that you go to your pharmacist, and when you ask for it, you get a set of capsules and the device, and the two of them together make the product. It's a combination product, but you have to change the capsule every time you have to take a dose. And then we've got the multi-dose devices, the famous discus, the laser doesn't work, on the left-hand side, which is based on the strip technology. So you've got packets of dose, which when you actuate the device or you perform some sort of action to the device, they move a position, pierce through the next packet of dose, and release it to the patient with their breathing. And then we've got the reserve ones, which are effectively, you've got a pool of powder and then some sort of scooping mechanism, precise scooping mechanism, that will allow and make the dosage available to the patient to inhale. Okay, so going back to Jamie's presentation, so all of the DPI particles are formulated with large molecules, and these molecules are carrier molecules, and mainly they're lactose. Now, there have been studies looking into mannitol for various reasons. However, the main carrier molecule out there, it is lactose. And there are two main reasons why. The first one is to try to bulk it up, so for handling, filling, etc., because the drug particles are too fine to be handled. And the second reason is that because of how fine the drug particles are, they form aggregates, so effectively kind of try to avoid having these aggregates into your dosage forms. And that's why you'll see that the DPI devices, many times, what they have is some sort of mechanisms to introduce shear and turbulence into the device, such as channels or little tunnels and torture tunnels that the powder will go through, and once it's inhaled, they will just separate the carrier molecules from the product. Now, there is a lot of regulation around DPIs, and these are a few chapters if you want a light night read, if you are having trouble falling asleep. But what I would like to highlight here is chapter 601, which is one of the main ones, and our USP is coming out with the 1603 and 1604. Whoever is interested, they can go back and have a look at them, and various US FDA guidance chapters and monographs. Now, all these chapters and all these regulators, what they describe from a physical testing point of view is two main tests: delivered dose uniformity and aerodynamic particle size distribution. And these are the two we will be discussing about today. So delivered dose uniformity, as is defined, is the delivered or emitted dose, which is the total amount of drug that was emitted from the inhaler device, and it's available to the patient. Now, is that one inhalation, two inhalations? It doesn't matter. It depends on the device. It will matter only during your testing. When you're performing this test, you need to make the necessary doses available to the capturing mechanism. Now, for the users that have performed testing of dry powder inhalers, they can see the number 4 appearing quite a few times, and it's a bit difficult to remember on the falls and what's going on. But the first 4 that you'll come across is the 4 steps that you need to use to set up your testing for delivered dose uniformity. So you'll need to set a P1, which is equals 4, and we'll see in a bit what this means. You'll need to determine the flow rate, check that you have achieved critical flow, and then determine the test duration. But let's have a look a bit better on what these 4s are. So these 4 kilopascal of P1 that you're setting when you're testing your product in QC or R&D environment is effectively describing the average pressure drop between human lungs and the atmospheric pressure, meaning that any person that is inhaling at any point, there is a vacuum created during this inhalation maneuver, and that will severely affect the delivery of an aerosolization of the product. That's why it's very important to set this pressure drop and replicate it in your testing when you're testing DPIs. Now, to determine the test duration, you'll need to be aware of the average human lung volume, which is 4 liters, and that's where this 4 comes from. But there is a bit of an inconsistency here because the USP requires 2 and the EP 4 liters, but that is something that, depending on which regulator you're following, you need to take into account when you're testing. And then there is device resistance. So every DPI is a bit different to each other. And with this being different, the resistance of the DPI is changing. Now, because the DPIs are passive, as we've described, this device resistance plays a big role as to how the testing and clinically the product will be delivered in the patient. Now, in this example, what we've assumed is a very low resistance inhaler on the top left-hand side and a higher resistance inhaler on the bottom left-hand side. Difficult when the pointer is not working, but I'll try to point with my finger. Now, if we assume that a patient is inhaling with the same inspiratory effort through the 2 different resistance inhalers, then that means that for the inhaler with a low resistance, they will be able to achieve very high flow rates because of the low resistance. Whereas with a high resistance inhaler, you will not be able to achieve such high flow rates, meaning that for a constant volume of the lungs V, it will take them more time to generate, as you can see on the graph on the bottom right hand corner. And why is that important? That is important because the flow rates and these speeds that are being sensed by the inhalers are very they're linked with a P1 at 4 kilopascal. And as a general rule, the higher the resistance of an inhaler, the lower the flow rate you require to achieve 4 kilopascal pressure drop, whereas the lower the resistance of the inhaler, the higher flow rates you will be experiencing. And you need to take that into account because you don't want to be developing, even if before you go into QC in the clinic, you don't want to be developing a DPI with very low resistance that requires the patient to be inhaling at 90 liters per minute if your patients cannot inhale at that flow rate. So everything makes sense clinically and also replicated in your testing. And some example devices here with low, medium, and high resistance is the rotahaler, the discus, popular discus, and you can see that the example flow rates match the test flow rates except for the low resistance device, which requires 180 liters per minute flow rate in order to achieve 4 kilopascal. However, due to the limitations of the testing systems and the impactors, then you need to perform the tests at 100 liters per minute. Another thing we discussed a bit earlier on is the critical flow, the P3, P2 ratio that has to be less or equal to 0.5. But what is that critical flow that we're all talking about? And effectively, the critical flow means that the air velocity through a restriction, which in our case is the solenoid valve of a TPK, of a critical flow controller, cannot go above the speed of sound. So what it really means is that any fluctuations upstream or downstream of the system will not affect the final flow rate that is sensed on the inhaler. So, and because of the flow rate and the importance of flow rate for DPIs, that is a key condition that needs to be met every time that someone is performing the test for DPIs. And then here we've got the equations for the timing, but it's just some simple equations. If you want to have a look at them, I'm sure the presentations will be available afterwards. So what does a system look like for testing of delivered dose uniformity of DPIs? On the left-hand side, what we've got is the sampling equipment. It's called the DUSA tube, where you can see the inhaler, in our case it was turbohaler, is mounted on. And that's where the dose will be captured. That's what you need to then take out, rinse, and analyze the sample with Hayes PLC. Then we've got a critical flow controller, which helps you with setting of the P1, understanding if you've achieved the P3, P2 ratio or critical flow, and then also a vacuum pump, which generates the flow rate. So it's pretty simple. The test setup, set the P1 at 4 kilopascal. You need to then understand, as we say, with the 4 steps, what is the flow rate that allows you to achieve this 4 kilopascal? Are we running under critical flow or not? And then finally, set your test time and run the test. And that was the first test, pretty straightforward. But now going into the more exciting bit, not that exciting at 5 o'clock, but aerodynamic particle size distribution. And that effectively defines how particles move in an open airstream. Okay, and this is a QC test that is performed regularly when you're having for batch releases every day in any laboratory. And the way you're assessing the APSD, so the aerodynamic particle size distribution of your products, is using an impactor. Now, there are 2 types of impactor mainly used, and with NZI being V1. So the next generation impactor on the top left-hand side, and the Anderson cascade impactor on the bottom left-hand side. Now, an interesting bit, and for whoever has experience with other devices, MDIs, nebulizers, what you see in these systems is a pre-separator. Now, the pre-separator in the red circle is used to separate the carrier, the large carrier molecules from the rest of the product in order to avoid clogging of the impactor. And then critical flow controller for the same reasons as used for the delivered dose uniformity, and vacuum pump for generating the required flow rate. Now, there are some USP monographs that are for some specific products that require you to use different pieces of equipment for testing. And that would be FP and salmeterol, so fluticasone propionate and salmeterol powders, for which you will need to change the dosage tube for the glassware you will see on the left-hand side. And on the ACI, you have to use the ACI with a specific fluticasone propionate pre-separator and induction port. And the reason behind that is that the original product that was put into the market, they were using similar pieces of equipment. So in order to prove equivalence, the regulators were requesting data to be submitted using the same piece of equipment. And it was the GSK initial products. We'll see here an overview of the DPI testing specifications. So what happens next? So we've done the testing for delivered dose uniformity, testing for APSD. We've taken all our samples, run HPLCs. So what's that? And there comes the data analysis, which is very important for these specific tests, as every other test. And I'll focus on the NGI, because here what is key to mention is that the NGI looks like a very big piece of metal, waffle maker, people call it, toaster, panini toaster, anything you can hear around the industry. But the reality is that no one understands how sensitive an impactor is. If you have ever seen an impactor, or if you ever come across one, when you open it, you'll see on the left-hand side, there are some stages with different sizes of nozzles or holes, as you can see. And the first stage, this is quite obvious to see the holes, even count them. But the righter you go on the impactor, the smaller they get. And these holes are very, very important, because the dimensions of these holes, they do define the particles that will be collected under every stage. Now, and this is called the cutoff diameter. So the cutoff diameter of the impactor determines what is the lower size of particle collected on each stage. Okay? Now, with the flow rate, the cutoff diameter of each stage is being reduced. And as an example, if we take stage 1, if we see at 30 liters per minute, the cutoff diameter for stage 1 would be around 12 microns, whereas if you run it at 100, if you run the impactor at 100 liters per minute, the cutoff diameter would be around 6 microns. So when you're performing your data analysis, you really need to take into account the flow rate that you're running your testing under, because otherwise you might be analyzing data with that you've run at 100 liters per minute, saying that the cutoff diameter for stage 1 is 12, so that will be all over the place, and you're risking batches being wasted for no reason at all. Now, some other key metrics that you'll see during this data analysis is the FPD. So I'd like to focus on the FPD, which is the fine particle dose. So that usually tends to be everything below 5. So everything below 5 tends to be the respirable fraction, meaning that's the size, the dose that will end up deep in your lungs, in your alveoli and terminal bronchus, and effectively have a pharmaceutical effect. And then also the combination of MMAD, mass median aerodynamic diameter, and GSD, geometric standard deviation. So the combo of the two describe your distribution. Okay? I've seen in quite a few laboratories that people set standards for either MMAD or GSD with ignoring the other, but the combination of the two describes the curve, not just one or the other. And a hot topic around inhaler testing is variability. It's not as simple as, like in the solid dosage forms, such as a tablet. You just take your tablet, pop it in a dissolution tester, and pretty much you're done. You just have to sample and put it into HPLC. Now, I've just destroyed completely the dissolution testing theories and problems. However, with the inhaler testing, it is a bit more difficult. And if you think about the clinical aspect of it, you've got the device, the formulation, and the patient to consider. It's not as simple as putting it in your mouth and swallowing it. So the testing also mimics this, let's say, variability. And there are many, many sources of variability, and that was a table from a John and Mitchell paper back in the day. But the bottom line is that the main problems with variability is that you will fail to achieve mass balance, and then you'll have errors in your APSD. And what that actually leads to, it leads to repeating your tests, your QC analyst doing things again and again, so low productivity, low morale. In case of MDIs, you need to keep shaking and firing, which can cause a few injuries. But bottom line is it costs. It costs to the organization, and you want to avoid it as much as you can. Now, if you take the first table I showed you with all the different variables and you kind of put it in a straight line with headlines, that is what you're going to end up with. However, they are interlinked. So you cannot just say that a method is a problem, because the method can cause problems to the analyst. And that's actually quite easy to prove. And here's where we get a bit more interactive, so please interact with me, otherwise it will be very awkward for me. So could you please raise your hand? Great. Now, have a look around you. All right? So that's a very simple instruction, very simple. Now, you can take it down, by the way. That's another point. All right? And that's every one of you. You've raised a different hand, a different timing, a different level, and some didn't even raise it. So it is very important that analysts are trained to the methods, and that the methods describe exactly what you want someone to do. So raise your right hand to this level for 5 seconds. So it has to be very specific. Otherwise, you get variability. And it's not always just the analyst's fault, let's say. Okay? Don't blame the analyst. But the whole aspect of variability is making sure that when you get an error in your results or something that you don't like, you're sure that everything else is eliminated and it's your formulation's fault. So you don't make any judgments on your formulation without considering all the rest of the sources of variability. Because if it was an analyst's fault, and then you go down your formulators and they start reformulating, that will cost you a lot. So now to be a bit more specific to DPIs, so a few variability issues is because of the powder particles are quite dry, they tend to bounce back and re-enter the stream of air in your impactors. So the way to counteract this, first of all, the way to identify that is by measuring interstage losses. That's a first bell at some extent. But also what you will see is shifts of the curve towards the lower micron sizes. And that will be part of the validation, and it has to be performed reproducibly during QC. So here, that's a completely made-up example of different coating methods. So with a red line on the left, you can see the red line on the right-hand side, which is purple, but it doesn't show. You can see the no coating, and with the coating, different coating material, you get shifts to the curve, and you need to decide which one is the coating solution that will work best for you. Yeah, the colors are a bit off. I'm sorry about that. Then the critical flow, ensuring that you're running under critical flow, it is vital. And that is a QC setting that you need to do routinely. Most of the times, you have problems with achieving critical flow when you have very low resistance inhalers, so you require very high flow rates for your testing. And when you're using the NZI in all of this, it's because of the resistances and the high flow rates, you get some issues with P3, P2, and there's a very easy solution for that, is to use a more forceful pump or connect two pumps to generate a stronger flow rate, effectively. Then we've got electrostatics. That is not my cat, I promise you. So powders, they rub on plastics of the device, and even different people in this room will have different static charges. So effectively, this will affect the deposition potentially of your product. So in order to do that, you just need to make sure that you use the necessary equipment for eliminating these electrostatic charges. And finally, we all know that powders tend to absorb humidity from the air. They act as sponges. And we have spoken with customers and analysts that have seen very minor differences in humidity, but they have caused big problems in the testing. And that's why you will see various capsules being held wrapped in foil, etc., when transported. But that's another thing you need to take into account. It's the environmental variability, and mainly with the powders is humidity. Now, in the last bullet, it was the system variability, so ensuring that you identify the high variable processes in your laboratory and using semi-automated equipment in order to make sure that you reduce the chances of variability and improve productivity and reproducibility. It is quite key. And then here we've got some examples of equipment. I'm not going to go through all of them because I think I'll bore you to death, to be honest with you, because it's not all relevant to DPIs. However, what I would recommend is the Dusha shaker and gentle rockers for DDU and APSD, as it's a good starting point and a standard for the laboratories nowadays. Train your analysts, and yeah, we don't need to do the training for you. You can do it for your analysts. Yes, we do have services available. However, make sure you train the teams, you train the analysts. Do not assume that something simple and easy will be well understood from new analysts. And of course, when you get into these big QC laboratories, not everyone is an expert in inhaler testing. Not everyone has experience in inhaler testing. And I know it's a very burdensome process to train someone new. However, it will save you a lot of time and energy down the road when everything starts going a bit. Righty, so I hope I kept it a bit short and it was interesting for a few, so I'm happy to take any questions.
Any questions?
This is a bit of a pre-drinks question, so I apologise in advance. Anna, you maybe answer a question that my asthma nurse couldn't. Will my inhaler behave itself at 5,000 metres?
Sorry?
Will my asthma inhaler act properly, behave itself, when I'm at an altitude of 5,000 metres?
And if you can inhale at that altitude, you'll be lucky enough. Well, that's a good question. I suspect there will be effects to that. And certainly what we've seen is that when you change, you will need to breathe in harder, I would say, because of the density of the air. And we have seen people transferring methods, funnily enough, from one area, from Brazil, let's say, to a very up in the mountains and a very low altitude country, and they've seen like major differences because they were using standard flow rates, but that's another story. So yeah, it can affect the performance, but as a patient, I think you'll just need to put a bit more effort into inhaling.
Oh yeah, I could bear walk forward.
Yeah.
And is there a minimum? I mean, I was camping at -20 in Ladakh at the time. So, at what point will the powders, fail to behave?
In terms of
in terms of temperature.
Of temperature, that shouldn't be a problem for powders. It's the humidity that's mainly an issue, and they will not fail. They will just not deliver as they are expected to.
Okay. Thank you very much.
You're welcome. Thank you for your question.
Any other questions? So thank you very much.
Thank you very much.
And thank you to everyone here.